Okay, great. Well, thank you for having me. I really appreciate the invitation, and it's nice to do something a bit different. So, a couple notes about myself. Mathematically, I'm working in geometric analysis, so I study things like soap films. So, um, geometry and topology in general. This project was a kind of a thought experiment for myself when I was in grad school. I knew of this result, but I wanted to try to find a really clear conceptual proof. A couple of the proofs I was aware of involve some manipulations where you pass to R2 twice, and then sort of go back to the sphere. And I was kind of wondering if I could, do something a little bit more unified. All right, so let me get started with the result. So probably maybe everyone here already knows it. So let me make a couple comments about notation. Let me just move this to the corner. Right, so I'm talking about vector fields on the two sphere. So the two sphere, I'm considering it embedded in R3, just the set of points in R3 that have distance 1 from the origin. So I've got my cartoonish picture here on the right. Vector field on the sphere V, what does it mean? It means to each point on the sphere, I'm assigning a vector in R3, and that vector should be tangent to the sphere. So I just mean this condition here. And so we do this at each point, and I'll draw kind of a cartoonish picture of a couple of points and their associated tangent vectors. So if you try to do this in a way that's continuous, and by continuity, I just mean, I could mean many different things that are all equivalent, but maybe the simplest is just saying that the component functions, the three component functions of this vector field are just continuous functions. So all this means is that if you move to a nearby point on the sphere, the vector will point in a close direction to the original point, in the sense that the limit as you move one point to the other of the values in one vector are the values in the other point. Okay, so the theorem says that no matter how you try to place your vectors on the sphere, if you do this a continuous way, you have to have a point where your vector has zero length. And so you can try to do this yourself, and you can imagine sort of where you might get stuck. Maybe the simplest, I'll try to sort of do this again. It's easy to see that you can find a vector field that vanishes at 2 points, and you can do this by, for example, imagining rotating the sphere. So I'm going to draw a lot of blue lines, rotating the sphere about an axis, say, and then your vector field are just the tangents to lines of rotation. So you would have lots of blue vectors like this, but then your vector field vanishes here and here. So that's just an example of a vector field on the sphere. So let me go to a quick proof outline. So this proof is not very difficult. I have this one-page sketch of the proof without rigorous definitions, but I hope a lot of the ideas. So I will quickly go through this one page here, and then attempt to go through things and put things on slightly more rigorous footing. So if you have questions about some of the notions here, maybe wait for a little bit, or mention something, and I'll say whether I'll clarify that notion later. So the proof is by contradiction. And the first set, without loss of generality, we're going to assume that our vector field has unit length everywhere. So we can just do this by, if our vector field didn't have unit length, I could replace the vector field with the vector field divided by its length at any point. And then I'd have a unit vector field. So this is just a matter of convenience. And then the main step is that to each what I'll call oriented loop, or just loop, on the sphere. So on the sphere, I imagine drawing a curve that has an orientation. I would like to associate what I'm going to call rotation number. Um, Here, the notation I'm using is n sub gamma, gamma being the loop. That's saliently an integer. And what it's supposed to do is it's supposed to track the net change in the angle between the tangents to your curve and the vector field at those points. So at any point on this curve, you can draw the value of the vector field at that point and the value of the tangent to your the velocity vector to your curve at that point. So this would be gamma dot, and then this would be v, the vector at gamma of t. And then you want to measure this angle, and this angle is changing. So the red and the blue are both moving as you move along, and this angle can be getting bigger or smaller, and you want to check um, basically the net change in this, which could be some integer multiple of 2 pi, and then this integer that we're tracking is basically that multiple of 2 pi. So it could be 0, 2 pi, 4 pi, minus 6 pi, whatever. Appropriately interpreted, you can consider it that. Yeah, if you had like a local angle, um, and then like the derivative of that angle, it would just be the integral of that. Yeah, if interpreted appropriately, it would be exactly that. The only subtlety here is just that, angle, we have to make sense of angle, not being a function on the real line. The angle is a function between 0 and 2 pi or minus pi and pi. And we have to confront this issue, and that we'll talk about the sort of standard way in basic topology to do that. But any number of different ways you could describe this that do make sense would be correct. So the salient features of this rotation angle, the first one is that with an appropriate notion of deformation of your curve. So if I have my curve on the sphere and I change it slightly to something, sort of a nearby curve, this rotation number is going to remain fixed. And the rough idea is that everything is depending continuously on your parameters, but this rotation number that we're tracking is integer valued. So if we have a continuous function whose values are in the integers, it has to be constant. So if we're mutating our curve, we're not changing the rotation number. And so now the game becomes taking a fixed curve and then deforming it in various ways so you can actually monitor, you can actually figure out what this rotation number is. So on your sphere, so red is supposed to be my little curve. If I take a curve and move it to be a tiny neighborhood, a tiny circle about a point on the sphere, things are looking more and more Euclidean. And then because my ambient vector field, my vector field V, is continuous, if I shrink this red loop tinier and tinier, it's very close to the picture where I just have a circle in the plane and my vector field is constant. And so from this, it's not difficult to see that for any loop which can be deformed from such a tiny red loop, the rotation number should be plus or minus 1, depending on whether you're sort of going around the loop this way or you're going around the loop this way. The first bullet point being that this rotation number you can define. I will explain that. I will explain it more. I have basically another slide that says this more carefully. So we should discuss that at that time. Yeah, so I have these tiny, bad, cartoonish pictures here, and I hope to have better, still cartoonish, but larger pictures later. So the second sort of counterpart to this is that if you have a great circle, you can do something rather interesting. So if I have my sphere here and I parameterize a great circle, let's say going around this way, I'm going to ask you now to look at my real screen here, not the iPad screen. So imagine I have a great circle. I can deform it in the following way through great circles. I can just rotate it around the entire sphere, and it goes back to the same great circle. However, if I'm tracking orientation the entire time, let's say counterclockwise rotation about the axis, I go back to the same circle, but now with the opposite orientation. And so if I look at what's happening to my rotation number for such a great circle, or what I'll call minus that great circle with the opposite orientation, oops, I am seeing that my rotation number is equal to minus the rotation number, because if I reverse the orientation, it's not difficult to see that if you locally watch how this angle is changing, the video you're seeing is just everything's going minus, everything's going the opposite direction. So this tells you that your rotation number has to be 0. And the last thing to show is that you can just deform one of these great circle curves to one of these tiny curves. And that's equally obvious because you can just shrink it like that. You can just go to the top like that. So now I'd like to discuss these points in more detail and try to be more honest and more rigorous about what are the issues about setting this up carefully. Okay. Okay, so what do I mean by loop? So first, I'm going to talk about things in R2 because that's where we set up the preliminary definitions, and later we will reduce to the R2 case. So what do I mean by loop in R2 for the purposes of this talk? I mean a map from the circle to R2. If you don't like circle or are not completely clear about what I mean by this, you could replace this with R and then just say that I'm 2-pi periodic in addition to what I'm saying here. So the salient points are that the velocity vector is continuous. So this is what is a C1 curve. It's the usual notation. So it's differentiable and the derivative is continuous. So we need this to make sense of derivative, but we need a little bit more. We need that the derivative is never vanishing, and we need this to make sense of an actual tangent line or tangent direction. So if you haven't experimented with the difference between these two definitions before, I can show you, very quickly an example of a curve that satisfies this, but not this. So here's the image of the curve. Has a corner, and there's no tangent line here. And I can make this a C1 curve have continuous derivative or even smooth derivative. I can make it infinitely differentiable. And roughly speaking, the way you do it is the parameterization slows down in a smooth way and actually stops as it gets here, and then starts up again as it goes over. So we want both of these non-vanishing conditions here and here. So this is usually what a curve satisfying these two conditions is usually called an immersed curve, or a regular immersed curve. Regular refers to this second condition. So the curve itself could intersect itself, so it could go like that, for example. Okay, so now I'd like to define the rotation number. And so again, intuitively, it's supposed to be basically what I wrote on the slide before. We have slightly simpler notions here. So what we have here is we're trying to track the angle between the E1, say, just some reference vector in the plane, and then the velocity vector of our curve. So in this example curve here, curve is going like this, and I'm drawing its velocity vectors. And so if, as I'm traversing here around the curve, I'm seeing the curve of velocity vectors starts out vertical here, and the curve of velocity vectors is moving around on the unit circle, and it just goes around once. And so here for this curve, the rotation number is going to be 1. This is still not a precise definition. I do this on the next page. Here, the rotation number is going to be 2. I've got my velocity vectors going around like this, and I'm probably not helping by even drawing them, but as you see what's going on as I go around like this, I'm moving around the circle twice, counterclockwise. Okay, so you can play around and find curves with rotation number, whatever you want, a positive or negative. What is the real definition? So for the real definition, we have to extract, we have to have a better notion of angle instead of a number between, let's say, 0 and 2 pi. We have to go to the real line. So what is the idea? How is this done in topology? So one looks at what's called this covering map. So you have the real line down here, and it's multiples of 2 pi, and you have this map that projects to the sphere. So this, the usual parameterization map, this cosine t, sine t map, and it's convenient to think of it and call it a projection map or a covering map here. And one of the points of this map is that for a small neighborhood about any point in the real line, if you take its translates by a 2 pi, you get this disjoint collection of neighborhoods, and all those neighborhoods project to a single little interval on the circle. And so this is called a covering map in general. So the point for us is that if we have this velocity vector that we had from before, the gamma prime, we can consider what's called a lift, a continuous lift of it to the real line. And what you want from this is you want the property that pi compose this gamma dot tilde, the thing that lives, that's image to the real line, is equal to gamma dot. So I'm trying to say with symbols something very clear, which is that, so again, I'll try to draw sort of the dynamic picture of it. As I'm traversing my curve, I see some curve on the unit circle, and I am tracking. So I start somewhere on the real line. So on the unit circle, let's say I went around twice. On the real line, I'm starting somewhere and then going around twice. In this case means that would be going around once, and then this is going around twice. So I actually stop not at the same point, but at some point whose difference from the original point is an integer multiple 2 pi. And so the correct definition, so first, the fact that you can do this, you can construct this lift with, I do need to say, so if I'm saying there's a unique lift, I do need to say that there's the lift starts at some point. Let's say this gamma dot tilde at 0 is in 0 to 2 pi. So I have some initial value, and then there's a unique lift. So the definition of our winding number, or our rotation number in this case, it's equal to, I take this lift, and let's say evaluate it at 2 pi, and then I subtract the value of the lift at 0. Is this making sense to people? Okay. So if you've taken maybe a point set topology course or done anything with algebraic topology, this is sort of a standard, very, very standard thing. And the why can you do this? It's simple properties about connectedness and continuity. So of course, I haven't actually given you a proof of this property, but it's not difficult. All right. So now I'm going to move on. Now I want to talk about this point that Max was raising earlier. So what do I mean by deformation? So what's called a homotopy, in this case, homotopy of the loops I talked about before. So I'm sort of using my own notation that's supposed to be tailored to this talk, but sometimes maybe the a correct phrase here would be maybe regular homotopy. What do we really want? So you have not just a single curve going, a single loop going from S1 to R2, but you have a whole family of curves indexed by a parameter that I'll call S. So I'll call S the parameter in this family and T the parameter along the curve. And so what you're trying to do is if I have, imagine for a moment that I didn't have loops, that I just had curves like this. I'd imagine my T parameter is sort of going like this, and my S parameter is maybe going like this. So I have sort of a family of curves like this that what I'm interested in is that the whole map is continuous. So I have continuity in this parameter and then also continuity in this parameter. And also importantly, each S slice, so each thing that I want to be, if I move in the T direction, a loop, I want it to be the type of loop I was talking about before. So in particular, if I move in this direction, I have a continuous non-vanishing velocity at every point. Um, so I claim that with these two conditions, the intermediate value theorem, and I'll try to say a couple more words about this, implies that whenever I'm at the sort of terminal curve in one of these homotopies, the rotation number is equal to the rotation number of the beginning loop in my family. Um, and this is because that this function, if I consider now, let me consider the function from 0, 1, interval 0, 1 to the integers, where f of s now is equal to this rotation number of the curve gamma s. So this is continuous because of this property. And oops. So the property 2 ensures that you can actually make sense of these rotation numbers for each s. So property 1 says that this function f, as defined here, is continuous. And now I have a continuous function from an interval to the integers. And so the intermediate value theorem says that my continuous function f hits any value, achieves any value between any two achieved values for my function. But my function can only achieve values in the integers, discrete set. So for example, if in this continuous family, my rotation number was 1 at some parameter and then -5 at some other parameter, the intermediate value theorem would say that this function achieves every real number between 5 or -5 and 1. But by the construction for NES, these rotation numbers are integer valued, so this is not happening, and I can only achieve that particular value. Okay. Is that making sense to people? Is that clarifying your question from earlier? Yes, yes. So this is a good and maybe an illustrative example because that's helpful for understanding homotopies in general. That idea is a little bit problematic for um, property two. And so I'm glad you brought that up because doing a simple trick like that won't necessarily preserve this property two that I really have homotopy through regular loops. So for example, here's an example of a homotopy of curves. I'll draw three or four pictures that would be bad for property two. So it's not going to satisfy this definition. So imagine I have a curve in R2, a loop in R2 that has a kind of smaller inner loop. I could imagine just shrinking that inner loop smaller and smaller so that it kind of pops at a point or becomes a cusp at some point. So if I'm doing that, if this is sort of the images of these curves and I'm varying in the S direction. So if I've drawn the image curves for four values of S, the initial S, so this would be S maybe equals zero, and then this would be S equals one. At the end, I have just the circle parameterized counterclockwise. But at the beginning, I had this loop-de-loop thing which, as we saw earlier, or as I tried to indicate earlier, its rotation number is 2 or minus 2, depending on how you parameterize it. So the problem here is that in the middle, at some point, I didn't satisfy property 2. So at some point, um, I either lost uh, continuity of my derivative or I had a vanishing derivative when this loop pinched off. Um, So I can't do sort of whatever I want with for example, like straight line homotopies like you were talking about earlier. Um, so maybe I will write down what you alluded to before. So if I have, let's say, gamma and sigma, two different loops, I could define, let's say, 1 minus s sigma plus s times gamma. So here is a clearly continuous map in S and T if the two loops gamma and sigma are continuous. And what I'm saying here is that it's not obvious by inspection whether property 2 is satisfied by this type of formula, because in order to check that the velocity is not vanishing, you have to do something a little bit nonlinear here. You have to take the velocity of each and then dot with each other and then check that that's not zero. Um, so later, when I consider my homotopies, it should be sort of obvious from the way I define things that property two will be satisfied. So I won't be using like a sort of algebraic formula just like this. Okay. Okay to move on? Okay, so now I want to extend things to the two sphere. So this is not terribly difficult. I will try to draw a picture about exactly what I mean. So what I want to do now is instead of talking about rotation number for a curve, a loop in R2, where my fixed reference direction was E1, I now want to do this for loops on the sphere, which now I'm going to have a variable reference direction. That's going to be this vector field V, this unit vector field V everywhere. So I'm going to try to think of V as like the E1 axis. So how do I mean to do this? Draw the picture first, and then I go to the notation to the left. So the picture is that at any point on the sphere, let's say on the curve that I'm looking at, so I already have the curve in red. So here's the point P or gamma of t. So I'm going to consider the tangent plane to the sphere at that point. And really, I want to identify that tangent plane with the z equals 0 plane in R2. So if I want to just imagine that this gamma of t is like the E3 axis, somewhere is the vector v at gamma of t at that point. It's in this tangent plane. And I want to think of that as like the E1 axis. And then somewhere else is this vector gamma dot t. That's also in this tangent plane. And so physically what I'm doing is I'm actually just picking up that tangent plane, moving it to the R, rigidly moving it to the R equals 2 plane with the gamma of t being the z-axis, mapping to the z-axis, gamma dot of t mapping to somewhere in the plane, and v of t, for v of gamma of t, that vector, mapping to E1. So notationally, my claim, so what data do we have? We have a point in R3, we have an two vectors that are orthogonal to each other in R3, which we can complete to an orthonormal basis in R3 by taking the cross product of the two vectors in some order. And once I have that information, I can rigidly move the point to the origin and then rigidly rotate the oriented three tuple of orthonormal vectors to the standard E1, E2, and E3 vectors. So this is supposed to be articulated in this panel to the left. So all I'm saying is that the you know, the blue vector is mapping to the E1. The cross product of the blue vector with what's supposed to be the z-axis. So this is the what will become the E2. So that vector here is going to be like there in the tangent plane. I'm moving that to the E2 axis, and then the position vector, which is orthogonal to the tangent plane, that's going to map to the E3 axis. And then that determines where my velocity vector is going to go. It goes somewhere on the unit circle in this plane. Now, all of this is depending on t. And so for every time, I'm watching my curve move around, and every time I'm just pasting things to the plane. And so at the end, I'm getting now this. So I can consider the curve phi gamma of t, v gamma of t, gamma dot. And so this is now a map from S1 to S1, where this is subset of R2. So I'm watching, really all I'm trying to do is watch this tangent vector, or this image of the gamma dot, which is now on this R2 plane. I'm watching it dance around on the unit circle. As I traverse my curve in my oriented direction, I'm watching this image move around in the unit circle. So I can talk about its rotation number, and that's how I'm going to define this rotation number of gamma on S2. It's going to be the rotation number on R2 as I defined it before of this curve here. So I've picked kind of clumsy notation, but that's what's going in the subscript there. Okay, so this is the definition of rotation number on the sphere. And now I'm going to consider, I'm going to try to articulate that family of curves that I was talking about before. So I have a two-parameter family of curves that I'm going to call CPS. So what is P? P is a point on the two sphere, and I think of it as determining an axis. So here's my point P. It determines an axis, and then the S is going to determine, so S equals 0 will correspond to, so CP0 will correspond to the great circle, which is halfway between P and minus P, traversed in the orientation that's counterclockwise or right-hand rule with respect to the point P here. So I traverse that great circle. And then for S positive, basically I'm trying to put the S axis here. So here's S and here's S equals 1, which I'm not allowed, would be actually this point. S equals minus 1 would be here. So I'm just measuring how far along I'm going along this axis. So here's a CPS for S positive, here's a CPS for S closer and closer to 1. Again, they have their orientations. So I'm claiming that this entire family of oriented loops, the CPS loops, that any two representatives of that family are loop homotopic or regularly homotopic, as I mentioned before. So this is clear, I think, from this picture if you fix a given P, because you can just change your S. So if you're at some S and you're at some other S, you just move through the S family, and that's clearly everything is depending continuously, and you have all the tangent vectors that you need. If you now want to vary the P, how can you see that any two loops are homotopic? Well, it would suffice again to consider the CP0 two loops like that. And you can see this is what I was trying to articulate before. You can just imagine continuously rotating the axis. So you're just moving the point P now around the sphere in a continuous way. So this entire family, this would be nice to have a nice animation, but I'm just rigidly rotating the sphere with all its oriented curves. And so that's absolutely fine as well. And so from all the preceding observations, any two CPS curves, they have to have the same rotation number. So let's just fix that number. Let's call it n. So n, an integer. And now we work towards the two cases we had from before. So if I have a CPS, and for that same P, I consider the C minus PS. So I do the same thing, but now I consider minus P, and this amounts to switching the orientation. If I had, going around this way for this P, if I choose the minus P, I'm going around the opposite way. And so if you think about the preceding, how this is defined, how all this is defined, you're seeing the curve that you see in R2 on the unit circle in R2. If you switch P to minus P, you're just seeing the same curve, but traversed in the opposite orientation. So this means that your number n is equal to minus itself, and so it has to be 0. Okay, but on the other hand, I tried to draw the cartoonish picture here in a little bit more detail. So I wanted to draw, to remind ourselves. So here's my sphere again, and I'm now looking at loops that are getting closer and closer. It's not liking my tiny loops. It's turning them into rectangles. So it's better. So I take tiny loop, and if I zoom in on that tiny loop, I'm seeing something I'm seeing a picture that is looking closer and closer to a picture where I have a circle traversed in counterclockwise fashion or clockwise, depending on the orientation, in R2 and a nearly constant vector field V. And this is, of course, using the continuity of the vector field V. So V is always in blue, red is always my curves and their tangents. And so when you transplant everything to R2 to get the rotation number as we defined it earlier, what you're seeing at any point is a small perturbation of just rotating. So the R2 picture is very much looking like you're just seeing a perturbation of this or a perturbation of this. Maybe it's wiggling ever so slightly and it's going like that, but you're going to rotate around 2 pi or minus 2 pi. That's it. Um, and so this shows that your rotation number is either +1 or -1, and that's the contradiction. Um, so that's all I wanted to say about the proof. If things I've said are unclear, I could try to draw more pictures. I have one more slide with just a couple, if you're not familiar with the background, a couple theorems that generalize this in one or two different ways that you might be interested in. Or I could draw some more pictures or try to answer some questions. Oh, I'm very sorry about this. Yeah, you're getting a different curve. Yeah. Yeah. Oh, yeah. So maybe your question is something like, are any two loops in S2 regularly homotopic? Um, so if I were actually a topologist, I would, be thinking better on my feet right now. So certainly you need something about simple closed loops. So the loops I've been considering so simple means they don't intersect themselves. Uh, so, I mean, for example, in the plane, if I have a simple loop, a closed loop, and you do a regular homotopy, um, the everything I've been saying shows that this rotation number is preserved. So I can't do a regular homotopy that takes me from uh, you know, this one to this one. And again, the that shows why that the thing that was here, the where you pinch off the loop to a cusp, that's why that's illegal. Uh, so I'm not really answering your question. Uh, I didn't. Yeah, I did something fairly soft, which is I just showed that a convenient family of circles are all regular homotopic. Um, but there are theorems that are of this sort that say that in topology that say things like if two objects have the same, two objects are homotopic or adjective homotopic, or only more if and only if they have the same blah invariance. So sometimes theorems like that are true, and sometimes there aren't. They aren't. Um, that's a good question. So probably all of these types of theorems are, sort of like I'm going to say simple, but that's not the right word. Basic topological theorems that hold for two-dimensional objects, like the Brouwer fixed point theorem and this theorem. Um, Probably they're all sort of equivalent, and maybe I've seen this before. I'm not sure I know an argument that I could tell you off of the top of my head. Um, yeah, passing from this to Brouwer fixed point theorem, or vice versa. Yeah, that's a good question. If you had asked me 10 years or 10, 11 years ago, whenever it was that I was, you know, really thinking about this argument, I might have had a better answer at that time. But I would guess that, yeah, probably this is sort of written somewhere. I don't know that a bunch of these things are sort of equivalent. But I don't know an argument off the top of my head. There are, of course, there are many different ways to prove all of these types of theorems, and some of the ways that I tend to like for some of these theorems, especially their higher dimensional counterparts, are using in the, let's say, smooth case, things like Stokes' theorem. Um, and but yeah, even there, I don't see like an immediate um, connection. But yeah, this maybe standard proof of the Brouwer fixed point theorem in a plane is also using winding numbers, so they're certainly related. Yeah, so I may have slipped into that notation. So winding number is what's happening on this slide here. This number that was called rotation number was tailored to this velocity vector. So as I defined it, rotation number is the winding number of the velocity vector. So more generally, if I have any map, let's say sigma from S1 to S1, and I can talk about this picture where if I have the curve and then I have the image curve, which is so as I move around on S1, I'm dancing around on my image, and maybe I'm going back and forth many times. But if I start and end at the same place, I can talk about everything that I was saying on this slide. And this rotation number, as I've defined it, is the special case of the winding number when the sigma. So in general, I could do, oh, it's not liking that. I could put sigma where I put gamma dot in all of these cases. So whenever you have a map from the circle to the circle, you're just trying to track the number of times it winds around the circle. Other questions or comments? Oh, Yeah, I'd be happy to interact with anyone else here more about this or anything else related. Let me know. Yeah, feel free to contact me later if you'd like to chat more.
Oh, I was gonna say I'm not familiar with ACL2R, but I'll have to check it out.
Oh, the Bonaktarski. I see.
Max, and who did it? Thank yeah, may I? Peter, thank you very much for this interesting presentation. I have not looked at these things for decades, but now maybe I do have a reason to look at it again. And let me just make a quick comment. Now, the theorem is obviously false if you replace the sphere with a plane. It's yeah, trivially. Now, and that leads us to the following question. What's the difference between the sphere and the plane? And there are many answers to that, but there's one invariant that distinguishes them, and it's called the Lusternik-Schnirelmann category. So this is a topological invariant. It's actually a number. It's an integer. And roughly speaking, this is a number, the smallest number of contractible pieces you need to cover your space. So for R2, this is just one piece because the whole R2 is contractible to a point continuously. But for the sphere, you need the whole sphere is not contractible. You need the northern cap and the southern cap. Okay, so that gives you the Lusternik-Schnellmann category. Actually, you need to subtract one in all the cases, but let's not worry about this. And the interesting thing about the Lusternik-Schnellmann category, it's actually related to complexity of calculations, and that was done by Stephen Smale, I believe, in the 60s, maybe in the 70s, where he looked at the algorithm of computing, finding complex roots of polynomials, and the complexity was bounded above by the below probably by the Lusternik-Schnirelmann of the something like a flow chart. So computer scientists should take notice of that. And circling back to your talk, I was wondering if one can actually employ this category, the Lusternik-Schnirelmann category, or more generally, the genus. There's also a notion of genus, the Schwartz genus, to do this kind of argument, because there are similar theorems. The fundamental theorem of algebra, that every complex polynomial has a root. You can do a homotopy theoretic proof of that. Or rather simple if you're willing to believe homotopy theorists. Okay, so this is just a sideline remark. It's and not even a rhetorical question, but I would be interested to see proof that would be built on that category, on the Lusternik-Schnirelmann category.
Yeah, that's a good question or good point. Sometimes there's sort of a yeah, I've heard of Luster-Nick-Schnierman category before, but it's never come up for me. One of the things I had on the next slide was that so a more general perspective that's I guess a little bit different is the Poincare-Hopf theorem, where you're still compact oriented manifold. So this wouldn't allow R2, where you can say, so this is a theorem that says that if you have a vector field with say, isolated or at most finitely many zeros, then it tells you basically what's called the index, which is so on the sphere, it would say that 2, which is the Euler characteristic of S2, has to be equal to the sum of the indices. So from 1 to k of the index of the vector field about the point pi. But it sounds like what you're saying about Luster-Nick-Schnierman category is maybe more, I mean, it's more fundamental than something like Poincare-Hopf because it's more directly related to sort of the structure of the space.
Let me dig out that paper by Stephen Smale, and I'll send it to Max, and he can.
Okay. Yeah, thank you. Yeah, sorry about that. I don't usually work with an iPad, and then I checked one out a couple days ago, and I made sure I could get the notes working, and made sure I could get to email and everything. I was thinking, oh, like it's gonna be fine, but I didn't. Yeah. Okay, great. Yeah, sorry, that's my bad. Okay. Yeah, thanks for having me again. So yeah, feel free to chat via email later. Take
Thank you all.